this next video, we're going to take you through a use case of how to perform an analysis inside of Improve. Let's say that you've received a data set from a data provider and you're working on this hypothetical project called DEF1002. You'll see here we have a new data set called example new.dat, and that's the data set that we're going to utilize to perform analysis inside of Improve. Let's say we're doing a meta-analysis. We can actually create a new analysis tree itself. Similar to what you saw in the workbench video, you'll see that a blank analysis tree will be created. We're going to go through and actually create a root step. We're going to use nonmem as the tool. We're going to utilize our local machine, utilizing version 7.2. As you saw in the workbench, we have the arguments which identify where nonmem is going to run, calling the command file and the output file being identified, which files to not bring back to Improve, and the streamable files. We're going to bring in files here. So first thing is the data set that we've been provided by the data provider. And let's say that we actually need to bring in some files. We have an example file here of a model file that's going to call example new.dat, and I picked that up from my DEF1002 folder. If I wanted to bring in a file from another folder on my computer, I could always right-click and open and import any files into this folder that I wanted to at any given time. You can see here I have the example new.dat. This model file here is going to generate a model1.fit, so fit table file from the results. This particular model is a proportional error model. And you'll see here, if we take a look at the data set, what the data set looks like. So we have concentration and, of course, amount evid time within this data set. We're going to go ahead and run this analysis against nonmem. We'll be able to monitor the iterations as the nonmem run is being completed. Once it's complete, we'll see that in the status bar showing finish unchanged. We can visualize things like the objective function value as well as all of the parameter estimates. Let's say at this point we actually want to generate a goodness of fit to see how this model actually looks when looking on a goodness of fit or a weighted residual plot. We can actually create a child step directly from the analysis step. Let's say we're going to utilize R for the goodness of fit. And let's say we're going to use our local environment running batch. We can in fact bring in, if you remember, we saw we had a table fit file that we're going to bring in. And let's say from our repository, we knew that we had an R script, in this case, which reads in model1.fit and outputs a weighted residual. This will run, and you'll see here we have a weighted residual that we can see. We can certainly come in and make any remarks that we need, such as at this point, we may very well want to go through the process of generating a new data set to be able to utilize in this analysis. So we'll come back to our tree. See here our nonmem step original as well as our R step. Let's say we want to utilize R. In this case, we want to test the capability to run the nonmem step utilizing the log of concentration rather than concentration. So we're going to go ahead and use R. We'll bring in the old data set. This data set, of course, has concentration. And we'll bring in a script file that we can modify, and we'll actually read in example_new.dat, and it'll write out example_logdv.dat, and of course that will come with the log of concentration in this new data set. Once this is run, we can take a look, and we do have a new data set which has a new column called lconc, and of course the log of concentration for this data set, for the concentration. We're now going to utilize this data set to run our nonmem. We'll go back to our tree, create a child step using nonmem. You'll see that improve will go ahead and bring in things like the location where you're running against, the instance. When you create nonmem to nonmem steps, it'll bring in the various arguments. It will also bring in the actual files that we want to utilize. In this case, we know that we want to utilize the new data set with the log of concentration that we just created in our previous step. So we can go to the analysis tree, go back to step 3 in the folders for this analysis tree. You'll see here the example logdv. We're going to bring that in. And then we need to make some modifications to the model file based on this new data set. First thing to note is we're going to call for the log of concentration. We're going to identify the $data correctly for this new data set. And then we'll make some modifications to the error model based on the change to the log of concentration. In addition, we can also add multiple processes to this environment so that we could run, say, goodness of fits or other plots and diagnostics that we'd like to run. So instead of creating a child step, we can create sub-processes. Let's say goodness of fit using R, using my local environment, and let's take the same R script that we used for goodness of fit previously. You'll see we'll read in model1.fit. In this case, we'll go ahead and this will be model 2, and this is going to be the log normalized model in terms of the weighted residual or the goodness of fit. So this will actually run nonmem, and then immediately after run R to generate not only the nonmem outputs, but also any R scripts or any commands that you're calling for graphs, charts, and diagnostics. We'll go ahead and run this, and this will actually kick off nonmem, and immediately after running nonmem, we'll run and bring back the results from the goodness of fit R script as well. You'll see here down at the lower status bar, it's running main. We'll be able to visualize the iterations and the result of that. And then we'll run the goodness of fit and bring everything back. So we can come and take a look at the inventory. If we take a look at this inventory, we'll see all of the typical output files that we'd expect, including the table file that we generated, and also the weighted residual, in this case the log normalized, which happens to be very much centered on 0 and no longer skewed. We also have the capability to identify special types of steps in the tree. We may want to identify this as our base model. This is going to be the base of what we utilize for the rest of our analysis inside of Improve. You'll see when we look at the tree, you can see the hierarchical nature of where we went through and generated the residual error model, we generated the goodness of fit, we generated a new data set, and we generated the new non-mem analysis with that log of concentration. We have the capability to visualize additional information about this tree structure. We can take a look at show properties and look at things like the description. You'll see here the proportional error model, goodness of fit. This actually allows you to see what you did in this tree itself, which actually allows for that tracking of the who, what, when, where, and why of your decisions. In addition, if I take a look at the tree run records, every one of the steps are identified here. In addition, if I take a look at, for example, run 4 has both a main and a goodness of fit portion, and that's also tracked all the way across, including where it's run. You could run, say, the main against a grid or a cloud, and then your local against, let's say, R or RStudio or something of that nature. Any of the other metadata that is tracked and stored is also tracked and stored across the sub-processes of, in this case, non-mem and R. We've taken through a typical use case of how to perform analysis inside of Improve. We've brought files into the environment. We've gone ahead and generated a new analysis tree, run a non-mem step against that default data set, as well as moved through and generated a goodness of fit to see how well that non-mem model file corresponds to the data set, created a new data set using log of concentration, and then utilized that log of concentration data set for a log normalized model within non-mem. We also have the capability to track where outputs come from. So for example, if we wanted to make absolute sure where that model fit file comes from, we are tracking at all times the parental association for that file. So we can actually see the exact version of the model file at any time, being able to visualize that model file, as well as the exact data set that was used and its location within the Improve repository. Everything is tracked at all times so that you never have to worry about what you are doing within an analysis. You worry about the gray matter in performing analysis, and Improve worries about tracking the who, what, when, where, and why.